So yeah, I'm Daniel from Bath University, and I'm going to talk today about my work on distance compression and how we're trying to approach to solve the problem of compression. So as a table of contents, I'm basically going to give an overview of the problem itself, then I'm going to go into our approach that we tackled to solve the problem, and I'll give a brief discussion of the experimental design, and I'll discuss some conclusions. So in order to give you a sense of concept, this work is focusing on audiovisual virtual reality as opposed to visual only or audio only. And what we're trying to achieve is there's a well-known problem in VR with respect to distance perception. In particular, it's how distances are compressed with respect to real-world scenarios. So if you're using VR to stimulate any kind of real-world context, people's perception inside VR seems to be skewed with respect to how they would normally perceive objects far away. So this is kind of just to demonstrate that if you have a scene where there's various visual information, various auditory information, what we're interested in is understanding and fixing the problem of how the brain uses this information to get a sense of depth. So some previous work has kind of looked at the problem in the audio and the visual domains separately. So for example, this work on the left here has thought, well, you can actually manipulate our sense of depth by changing what's called the angle of incidence to both ears. So in spatial audio systems, if you're not familiar, the system here, for example, could be used for what's called a binaural system, which essentially renders audio by delivering signals to the left ear and the right ear separately together, and this kind of creates a sense of the audio source coming from particular positions in space. And what we see here is that if you just change the angle, what we can actually do is we can actually use that to manipulate the distance to the source. On the right-hand side, we see some work that was looked in the visual domain, which focused on changing the geometry of the scene in order to impact our sense of depth. This study in particular tried to see what the responses people gave to the distance from themselves to the book, and what they found was that in the lower scene, where the geometry has been modified, the people were more accurate in this perception. So this is just kind of give an idea of the various domains that distance perception seems to be compressed, and we have focused on kind of combining these two into audiovisual. So the approach we took is kind of on loan from a theory in psychology called maximum likelihood integration. So essentially what we have here, this you can imagine if for a particular percept you have a bit of audio information, a bit of visual information. And what we believe the brain does is it combines this information to get a kind of a global mean, which is the Gaussian curve in the middle, and it takes this as its kind of a global information and then as a percept. Below that then is what's called a psychometric function, and this is basically like an ogive curve, which basically shows how in the middle is the 50%, which is the chance or the point of subjective equality. And as we go up higher, we see that people are more accurate in making a response, so up to the top right-hand side of the curve. On the right-hand side of that image, what we see is that, well, imagine if you are in an environment where one modality is receiving more reliable information than another. So in this particular example, the audio information is a much more flatter curve, so it's a little bit less reliable. There might be some noise in the signal. On the right-hand side, the visual is much more reliable, so the global percept has been shifted towards the visual domain. And on the bottom, what we see, what the psychometric function is, it actually shifts it over to that mean value. This is basically saying that when the brain has two conflicting sources of the same information, it kind of takes the best of both worlds, and it opts for the most reliable source. So this is adapted from an early paper from Ernst and Banks, which kind of was the first to kind of show that the brain operates in this statistically optimal fashion. So, in order to study compression, what we did was we looked at a series of papers in the past and have tried to model how people compress distance, or rather how they perceive distance inside virtual scenes. This equation at the top here is basically represents a curve fit from Anderson and Zahorik back in 2014. So what we did was, okay, so if this equation here dictates the what you perceive. So phi here in the center is the position of the object. Okay, so constant alpha is a power factor. The y hat is what you perceive. So if phi is the actual position of the object, y hat is the position you perceived. So what we can do is, if we flip that equation around, we can then have, it changes the semantics a little. So what we now have is, we have a position that we want you to perceive, and an actual position of the object. So for example, we want to find the position that we should render the object at, knowing that this is the y hat is the position you would perceive. So we've essentially just kind of tilted the equation on its head in order to deduce the location that we should render the object. Okay, so to put that in kind of a less mathematical term, what this basically gives us is it gives us a function to determine positions of objects in space and how we should render them. What we get here is, I don't know if you can sort of see that very well on the projector, it is essentially you have an incongruency effect in the audio and the visual components of an object in VR. So for example, the visual component is rendered at a certain position, but the audio is effectively pushed back based on that equation that we saw earlier. So what we've actually done is we've actually separated the acoustics and the visual geometry of the space in order to create an incongruent environment that is more perceptually accurate with respect to this compression problem. So our two main hypotheses were that we would render an incongruent environment, and this would result in a more accurate distance percepts in VR. The second one is kind of a reproducible effect from the Ernst Bank's paper, saying that as we increase visual noise in the headset environment, we expect people to then rely more on the audio. So this is basically that we can verify that this statistically optimal theory is indeed working. So therefore, we can use it to analyze our results. So on to an experiment. So in order to do the experiment, we have to write some software. So this here is essentially a spatial audio plugin for the Unity 3D engine. So it operates, has a C++ layer here, which is essentially your file I/O in from the side, and there's a sound bank, a spatializer in there, and an actual codec to actually send out the audio to the headphones. And then that sits alongside the Oculus Rift SDK, and we combine them to C# layer to Unity. You get a full system that enables you to develop 3D audiovisual environments. So the actual experiment itself then, so we went for within subject's design, and emphasised this what's called a two alternative force choice. So the task was people would receive a virtual audiovisual object. It would appear at a location, then it would disappear, then it would appear again at a slightly different location. And what we asked people to choose was the one that they perceived closer to them. So as they were doing this task, certain conditions we would manipulate the incongruency of the audio and the visual component. So some conditions both were the same, so we applied no incongruent compensation. In other conditions, the audio was indeed pushed back with respect to the visual. So that resulted in 9 conditions, essentially 6 audiovisual, which we modified the noise level in the visual signal, 3 congruent and 3 incongruent, 2 audio only, and then a visual only for control comparison. So what we get here is so this is just graphing a subset of that data with respect to the audio-visual noise conditions. So this is essentially the noise level 1. There was a minimal level of Gaussian noise added to what people saw inside the headset, and as we degraded that further, the curves seem to kind of flat out. But what I want to point out is that this is the congruent condition. So this is what we would do normally if we weren't manipulating the environment at all. As we shift over to the incongruent conditions, we can see that the curves change slightly. So what we get here in the far side is a slightly more steeper slope than the previous slide. What that means is that as the slope of the psychometric function increases, that means that we were getting more accurate. So as we modified on the x-axis the distance from the person to the virtual object, they were more accurate as that discrepancy was smaller. So for a less accurate result, we would expect to see a flat curve like this, to say that it took a while before people became very accurate. A steeper curve like this means that within a couple of millimeters, a couple of centimeters, people were immediately as accurate as they would be in the real world. So this is our incongruent fits. To kind of tabulate that might be a little bit clearer. What we see here is that so we found, people have alluded to before, frequentist tests are you've got to be careful, but we found a relatively small effect for the incongruent conditions with respect to the means between the far range for both congruent and incongruent. So the effect was more prominent when objects were further away. When objects were closer to the person, the compensation for compression didn't seem to operate as strongly. Then we also just did some kind of line correlation analysis just to show that the actual method is generalizable across population with respect to previous viewer use and video game play. So what we don't want is to basically design a system that is really only applicable when you play lots of video games or you use VR an awful lot. What we would like is a system that basically enables you to put on a headset and you're immediately perceiving the world as you would normally. So there's very minimal kind of transition period between real world and virtual world. So to conclude upon that, as I said before, no correlation between viewer play, computer game experience and the compensation function. As I said, method compensates successfully, but only for objects that are far away. So we can try to explain this with respect to previous work that has identified a rough estimate of 3 meters from the observer, which gets to a point where after that objects seem to be compressed further. So our method seems to compensate for that. But when you actually pass that 3 meters point towards yourself, people actually start to overestimate distances. This again has been linked to a fight or flight evolutionary term. So it actually makes sense to overestimate because it gives you more time to react to something approaching you. But again, this is highly, we haven't done any of our own studies on this. This is just trying to speculate as to why the results are in this way. Finally, of course, the method is adaptive. So we literally operate at the software level. So we just modify the position of that the audio is rendered. Therefore, it's immediately, you can implement it straight away into any viewer system that you currently have. So yeah, just to finish up, I just want to say thanks. This GitHub URL here is, I've actually got permission from the company to release this source code. So if you are interested in designing spatial audio systems, basically what this will give you is a drag and drop plugin for Unity that basically enables you to just specify file names for audio sources, and it'll just do all its rendering at runtime for you in the background. So if you are interested, check it out by all means. And that's it.
Great, thanks so much.
So yeah, welcome questions, I guess.
Same drill as before. You have a question, you go to the front, you say your name, and then you help Eamonn change the world. Check that the mic is on. Tap it.
Yes. Hi, Miguel again. I wonder whether these breaks at some point.
Yes, indeed. So we go up as far as 10 meters, which, yeah, I guess is arbitrary, you could argue. And so, indeed, it would be interesting to see how far, to avoid a pun, you could take this.
So, do you expect these to affect kind of like the immersiveness experience as well, rather than just kind of like your perception of distance?
So, the angle we're spinning on this is that it would be wise to apply this sort of method if you're using VR for productivity. So if you're an emergency service response team, any sort of context that demands a veridical perception of space, this method would be highly applicable. If you're using VR for entertainment, it's arguably not as mission critical, but I haven't got any data to show that it did impact immersiveness or sense of presence, but it would be interesting to observe that.
Nice to study. Thank you very much.
You're welcome. Thanks.
I have a question, and I'll try to make it loud so other people can hear it. So I'm fascinated by the crossmodal approach to enhancing VR, really promising, I think. In the physical world, we probe the world in a dynamic way, so we negotiate with it, don't we? So
Indeed.
we might cock our head like this, or look around. Have you thought about dynamically, or taking account of those dynamics as you adapt the audio playback or the visual playback?
Yes, so obviously this work is a year old now, more or less. We've actually, there'll be publishing a paper hopefully next month or the month after that in the journal that has looked at more realistically rich environments. So essentially because in our experiment it was very abstract with respect to pink noise audio stimulus and a green cube. But now in a study I did last December, we have more naturalistic cues to distance. So we wanted to control for the cues you would get. So all you got was size of the visual and intensity of the noise. And then I'm also next month doing a study into more dynamics, so with respect to reverberation and motion in VR. So hopefully next year, 2017.
I think it'll be very, very interesting.
Good, thanks.
Okay, so let's thank Eamonn again.